Okay, so there was this word closed and bounded set. Okay, so I want to draw you some closed and bounded sets. The first closed and bounded set that's easy is a point, right?
Oh, I got you. Yeah.
Maybe let me do this. Closed and bounded sets, things that are not closed and bounded sets. Cool. So the next, maybe easiest closed and bounded set is just take a disk and fill it in. You guys all with that? Okay, so a not closed and bounded set that looks similar would be a
Disk without closed ends.
yeah, a disk without closed edges, right? You guys see that? This would be like the temperature within 5 feet of me, including 5 feet from me, versus the temperature in the atmosphere. Like, I don't know where the atmosphere is. It's weird. It just kind of fades out. You guys good with that? Rectangles are also easy closed and bounded sets. Make sure you include the edges, all of the edges. Things that are not things that are not closed and bounded that look like rectangles might be a rectangle without one edge. A rectangle where you leave out one of the corners. A rectangle with a hole in it. I'm here envisioning 1 point removed. You could also do something really stupid. You could like take a rectangle and take an open disk out, or take a closed disk out to leave you an open hole. Right, you see those kind of, you can't get at that edge there.
If you took a closed disk out, would it be still down?
If you did this, you mean?
Yeah.
Yeah, if you left the edge in, and the way you leave the edge in is you take an open disk out.
Yeah.
Does that make sense?
Yeah.
So if you take an open disk out, that leaves the edge in, and this is closed and bounded.
Oh, yeah.
But this guy where you took the edge out too, that one's not closed and bounded. You guys see this?
Yeah.
Other things that aren't closed and bounded are stuff that looks like this.
How's the point? Is that point supposed to be dotted, or
What point?
is that point, because it, yeah,
That guy is 1 point, one solitary point removed.
okay. And
So that's like just a minuscule hole punch, right?
But you don't know what, like, it could have
It could have been.
Yeah, and I don't know what it could have been.
been. Okay.
Right, really that would be like you take some surface that you know has a peak at one point and say, but you're not allowed to go to the top. Like you can get as close as you want to the top, but you can't actually stand on the top. You guys cool with that?
Mm-hmm.
Taking the peak off of mine.
Or you could have an asymptote, right? You guys recognize that from the one we had earlier? Where we had like 1 over r squared. Right, that thing's continuous on some closed rectangle except at 0, 0. But it doesn't have a maximum value there because you can run up that asymptote as high as you like. You guys kind of see that? Okay, so there's lots of ways to break bounded too. You guys see that? So anytime you're allowed to run off to infinity, it doesn't matter whether that running off to infinity narrows down. So like if you did something like this, where those get closer and closer together, that's still not bounded. You guys see that? Okay, so little flavor. Hopefully most of these in our examples here for at least a little while will be rectangles and circles.
It doesn't effectively hold water. It's not bound.
Yeah, good. If you couldn't pour water into it, if you couldn't fill it with a finite amount of water maybe,
does.
right? You guys see that?
You
Yeah.
get full water.
Can't we have unbounded edges with, or like Gabriel's form has like,
So it is possible to get results that look a little bit like the extreme value theorem, right? Like, let me say this. Just because something doesn't satisfy the extreme value theorem is not enough to know that it doesn't have a max or a min, right? So, for example, like Calc 1 style, like here's a function that has a max and a min value,
But you can't.
and it's continuous on an unbounded set. You guys see that? So like, this is a little bit. If A implies B, you need to be a little careful because not A
Does not imply.
does not imply not B. You guys see that? Some of you guys did this with differentiability and limits on your exam. I asked if a limit existed. You took the you took the partials and said the partials don't work, so the limit doesn't work. You guys see that? That's not actually enough. If the partials had worked, you would have known the limit would. But knowing that the partials don't isn't enough for the limit not to work. You guys see that? That's like the absolute value function isn't differentiable, but it is continuous. Cool? Questions? Thanks.